Hello, I'm David Pellerin of Impulse Accelerated Technologies, and this is Finding Nemo in streaming HD video using a Xilinx FPGA and the Impulse Co-Developer C-to-FPGA tools. What you've been looking at is a demonstration that we recently presented at the Consumer Electronics Show featuring our Impulse FPGA development tools and the Xilinx Video Starter Kit. The goal of this demonstration was to show how C2 tools combined with the Xilinx provided video reference examples and tools can be used to rapidly prototype and deploy a complex video processing application at CES. What we're doing is analyzing a video signal as it passes from the DVD player through the FPGA via DVI interfaces and to the monitor you see here. For every pixel in every frame, we're looking for a specific target pattern, Nemo's distinctive stripes. When we find that pattern, we assume that we've found our target Nemo. We use the target location information to lighten or darken pixels in subsequent frames, creating the spotlight effect you see here. All this is done without slowing down the frame rate or degrading the video signal in any way. To make this work, we need to perform a number of complex parallel operations at a very high rate. These operations include color comparisons, geometric calculations, keeping track of Nemo's location and setting the location of the spotlight. We also need to do some simple pixel filtering, all within the time it takes for one pixel to fly by in the video stream. At a resolution of 1280 by 720 or 720p at 60 frames per second, that's well over 55 million visible pixels that must be analyzed, compared, calculated, and filtered each second. How did we do this? By using the Impulse software to hardware compiler and the parallelism of an FPGA. The hardware we're using for this demonstration is the Xilinx Video Starter Kit, equipped with a Spartan 3A FPGA device and various I/O interfaces, including DVI input and output. Xilinx provides a number of reference examples with this kit, including a streaming video filtering example that we've used as the basis for our demonstration. Using the reference example and the Impulse tools, we were able to quickly assemble a system for processing video in real time, using a combination of Xilinx Platform Studio, Xilinx System Generator, and Impulse Co-Developer. The data flow through this FPGA-based system is shown here. Keep in mind that all of these elements, including the Xilinx Microblaze processor, are contained within the single FPGA device. The Impulse design tools greatly simplify the creation of a complex application like this. The Impulse compiler is capable of analyzing and optimizing C language routines and generating parallel pipeline hardware that's ready for use with the Xilinx tools. The Impulse C-to-FPGA tools and libraries can be used for a wide variety of applications, ranging from simple ones like this to very complex applications involving many connected processes. For our demonstration example, we have two basic functions that need to be performed: determining Nemo's location and creating the spotlight effect. To keep this simple, we've decided to perform both functions in a single C language subroutine, in fact in a single loop. Various variables local to the loop are used to capture needed information pixel by pixel, line by line, and frame by frame as appropriate. Let's see again how this works. That's fun to watch, and the coolest part of this example was that it was written and deployed with just a few days of work. To find Nemo, we need to find a combination of pixels that closely matches some distinct feature, in this case one of his stripes. We aren't too picky about which stripe, nor are we concerned about whether it's really Nemo we're picking up or his dad. A real-world application, for automotive safety for example, would probably use more advanced and accurate methods of object detection, such as particle filtering. That kind of algorithm can certainly be done in an FPGA and using C-to-FPGA tools. This example is substantially simpler, but it does provide some idea of how a more complex algorithm can be created and how hardware parallelism provides the needed performance. So let's see how this demonstration was created. First, we used Impulse C to describe the basic algorithm. The code for stripe detection is pretty straightforward. Although we experimented initially with a 9x9 pixel image kernel, which requires buffering at least 8 scan lines, it turns out that we only need to look at one scan line at a time to find a vertical stripe. The pixel data comes through as RGB values in a data stream, so we need to choose some ranges and combinations of red, blue, and green that we can categorize as white, black, and orange, the three colors that indicate a stripe. By the way, one improvement we might want to make later is to convert the RGB colors into an alternate format that provides luminance information, allowing for better quality detection in darker and brighter scenes. But as I said, this is a demo, so we can keep it simple. For each scan line, we'll be looking at a sliding region of 12 horizontal pixels. One side should appear orange, and one side should appear white, and a darker area should be found in the center. If the band of pixels is wide enough and we choose a good rate of RGB colors, then we'll be able to pick out Nemo when he's bigger and when he's smaller, and avoid getting too many false positives from other orange, white, and black objects. For the spotlight effect, what we'd like to do is have fast, but not instantaneous, movement of the light toward the target location, and a slower movement of the spotlight back to the center of the frame when Nemo is not found. This will help to keep the spotlight from jumping around too much, or jittering as it fixes on different stripes, and it will make the demo just look smoother overall. The size of the spotlight is set at 600 pixels. That's big enough to catch Nemo no matter which stripe we find, yet small enough so we can see the light move around. We also need to describe how the video pixels are read in and written out of our algorithm. Fortunately, Impulse C includes predefined functions for streaming data, such as the co-stream read function shown here. In fact, the Impulse co-developer tools take this abstraction one step further by allowing streaming interfaces such as this to be automatically wrapped in platform-specific interfaces, as we'll see in a moment. After the algorithm has been initially described, we can use standard C tools such as Microsoft Visual Studio to debug the algorithm and verify correct behavior. For this example, we've chosen to simulate the video image filtering using a C language test routine. This test routine reads in single frames captured from a movie in BMP format. The pixels from this test image are sent through the filter, which at this point is compiled as software on a Windows development machine and then written out to a new BMP file as shown. Using standard C tools such as Visual Studio for debugging of complex algorithms before targeting hardware is a huge benefit of using higher level tools. In this case, we're able to modify the pattern recognition algorithm, recompile and test the algorithm in under 2 minutes. Doing the equivalent algorithm testing using lower level hardware design methods would be far less productive. Once the basic algorithm is working, the next step is to compile the code to hardware using the Impulse C-to-FPGA compiler. The compiler is capable of generating pipelined parallel hardware from sequential C code and can be directed to generate hardware with varying degrees of parallelism. Because we're processing video data in real time, it's critical that our application run at pixel rate, meaning a loop iteration rate of 1 pixel per clock cycle, and at a clock rate of 75 MHz or better. Getting this kind of performance from a complex C language algorithm can be easy or it can be challenging depending on the nature of the algorithm and the coding style used. Fortunately, the Impulse tools include interactive and graphical tools that make it easier to see the results of various methods of coding and to iteratively optimize and refactor the code to meet performance goals. After the optimization phase, the generated hardware can be exported from the Impulse co-developer environment and imported into the Xilinx Platform Studio tools for synthesis, placement, and routing into the FPGA. This is where the Impulse-generated filter code is combined with other parts of the system, such as the microblaze processor, to create a complete application. The automatically generated DVI streaming interfaces make this part of the design process quite easy. All that's left now is to download the bitmap to the FPGA and start the show. This has been a brief but fun example of how the Impulse co-developer tools can dramatically accelerate development of high-throughput video applications. For additional information about Impulse products and services, please visit the Impulse website. Thanks for watching, and remember, just keep coding, just keep coding.